In this video, we're going to examine the phenomenon of angular momentum. This is going to be just like every other angular version of a variable that we've looked at before. It's going to follow all of the same rules that momentum followed. It's just going to be moving in a circle. And if we want to work with angular momentum, that is going to be represented by a capital L. It's got two equations. One is going to be the moment of inertia times the angular velocity. So that's basically our rotational mass and our rotational velocity, which makes sense for our rotational momentum. And it's got momentum times the radius that the momentum is going at. We can easily convert from tangential momentum, which was m times v, to linear or angular momentum just by multiplying it by that radius. So just like we were doing with velocity to angular velocity. So in this first problem we have here, we have a disk that is rotating on its own. And we have a second disk, that's going to be this guy right here, that is dropped onto it. This second disk is initially motionless, but after it drops on, the two will spin together. And so this is really a collision problem with angular momentum. We have an inelastic collision. The two objects are going to be stuck together and they're going to move together with a final rotational velocity. So how could we solve this? Well, our initial spinning disk is going to have a momentum L. So let's write this out. It's going to have a momentum L, that'll be our initial momentum, and that'll be equal to the final momentum that the two disks have together. So I can write it like that. Now, what I need to do here is I need to break this out into my L naught. My L naught is just going to be this disk here. That's going to be its moment of inertia times its angular velocity, and the angular velocity naught is given here. It's 15 radians per second. But the moment of inertia, I'm going to need to find that using an equation. So this equation for the moment of inertia of a disk is 1/2 mr squared. So I'm going to plug that in here. I'm going to have 1/2 mr squared times omega naught. And that's going to be my initial angular momentum. Now, what's my final angular momentum going to be? Well, that's going to be the moment of inertia of both of the disks combined, which is going to be this I, which was 1/2 mr squared, plus, and we have the definition here, the second disk has 1/2 of that moment of inertia. So it'll be plus 1/2 of 1/2 is 1/4, and then it'll still just be mr squared. It'll be the same, we'll use the same variables for that because everything else will be halved because of that 1/4. And then all of that times my angular velocity. So that's my general equation. So I can plug everything into that. So I've got 1/2 and m, which is 5, r, which is 0.3, squared. And then my omega naught will be 15. And then here I've got 1/2 of that same 5 for m and 0.3 squared plus 1/4 5.3 squared. All of that times omega. And omega, this is what I'm looking for. So I'm going to put all of these numbers together, and then I'll be able to solve for omega. So what I end up with is 3.375 equals 0.3375 omega. And then I just divide both sides by 0.3375, and I get an omega being equal to 10 radians. So that's how I solve this problem. My final omega is going to be 10 radians per second. So let's try another one. So this problem is a little bit different. I have this purple ball being thrown and caught by this turquoise arm. This turquoise arm has a mass of 2 kilograms. It's got a radius of 1.5 meters. And we're going to say the lever arm of this has a negligible mass. And so this is effectively just a point mass spinning at a radius, which gives us a moment of inertia of mr squared. This purple ball starts with a velocity of 45 meters per second, and this catcher does not have any initial velocity. And so our ball is going to run into this, and then together those are going to spin along this axis, with this being the axis of rotation. And so once again, I'm going to have my initial momentum will equal my final momentum. Well, my initial momentum is really going to be a linear momentum. How do I convert that? Well, the moment this ball hits this mitt, well, it's going to be at a radius. So we can still use that same radius. We just say at the moment of impact, it's going to be at this radius from its point of rotation. And so we still take that initial momentum and we multiply it by that radius. Then after that, they're going to move together. And so we're going to have a final moment of inertia times omega. And so this linear momentum can be broken up into m, v, and then we've got that r there. We get I omega. So now we can just plug our numbers in for this. So we've got 2 for a mass, and our initial velocity is 45. It's going to be at a radius of 1.5. Now, what is my moment of inertia going to be? Well, after these two collide, they'll be moving together, and so the mass will be 2 kilograms for this section of the mitt. It'll also be 2 kilograms from that guy right there. And so I'll have mr squared. My mass will be 2 plus 2, which is 4. So 4 and then 1.5 squared. So 4 times 1.5 squared times omega. And that'll be how I find my final omega value. And so I just multiply all of my numbers together. And when I do that, I get 135 on my left side. And I get 9 omega on the right side. So I'm going to divide both sides by 9. And I end up with 15 radians per second for omega. So my final angular velocity is 15 radians per second. Pretty straightforward. So now let's do kind of the reverse of that one, where I've got a hinged rod that is going to fall and hit a ball, and that ball is going to move over with some velocity. Now, this hinged rod is going to be a rod, and so we're going to have a moment of inertia for that rod, and that's going to be 1/3 ml squared. The length of the rod times its mass times 1/3. That's going to be a rod spinning about its end. And with that, we've got a initial angular velocity. Now, that means we're going to have an initial angular momentum. And that's going to be equal to our final angular momentum. Well, what's our final angular momentum? This is going to be moving linearly. We're going to do the same thing we did last time. When this starts to move, it's going to start to move based on this radius being struck right there. And so we're going to say that this L, this final momentum, is also equal to the final linear momentum, which will just be mv, and then we'll multiply by an r to make it angular. And so we can still use that same r. And so now our initial angular momentum, that's going to be I times omega, which I is going to be this 1/3 ml squared. So I've got 1/3. Then my mass is going to be 10. My L is going to be the radius here, 0.75. And that's going to be equal to my mvr. And then my mass of that ball, since the rod is no longer moving, I don't need to account for its mass, it's just the ball that's moving. It's going to be 0.2 for mass. V is what we're looking for, and then that radius, we're going to keep using that same radius, so 0.75. And so then when I multiply those values together, I get 28.125 being equal to 0.15 V. Now I divide both sides by 0.15, and I end up with 187.5 meters per second for my final velocity. So there's some angular momentum problems for us. Now, there is one other type of problem that we might encounter. So here's a fairly common problem with angular momentum. We don't have a collision, we don't have our object changing really its mass in any way. All that changes is the radius associated with that object. When that radius changes, the moment of inertia is going to change. And because that moment of inertia changes, our angular momentum has to stay consistent somehow. It has to be conserved. And so what happens is our velocity will actually change just because that radius changes. This is really common in orbital motion. We have a planet revolving around the sun here. And so this planet has a really exaggerated elliptical orbit with a radius at our starting point of 1 e30 meters. It's got a mass of 1 e24 kilograms and a velocity of 1 e10 meters per second. So we're going to have our initial and our final angular momentum being equal to each other. And both of these are going to be based on mvr. There's three variables. So we can say the mvr here, well, that's going to be 1 e24 times 1 e10 times 1 e30. And that'll be equal to the angular momentum here, which our mass doesn't change. Our mass is still going to be 1 e24. Our velocity has to change because our radius is changing. It's going to be 1 e28. So what's nice about these kinds of problems is that mass just cancels right out. We just divide it out. And so all that we have to consider is how VR equals VR. Should be pretty straightforward. So let's figure that out. Let's take our 1e10, or 1e10 times our 1e30, and divide both of those by 1e28. And that gives us a final velocity of 1e12 meters per second. So these are usually pretty straightforward problems, but there are other ways that we see them, not just in orbital motion, but if we have something like a figure skater. If a figure skater is dancing, and I'm just going to draw a stick figure here, is spinning. She's spinning with her arms out, and then she brings her arm in. Well, if she brings her arms in, suddenly her radius changes. And if we look at this is a very different radius from this. It's about half the radius. And so her moment of inertia would change. And so proportionally, her angular velocity would have to change. So her omega would have to increase. And we see this all the time in Olympics. Every time we have a figure skating competition in the Olympics, someone is going to be doing this move where they pull their arms in so that they begin to spin faster. And this is something that we can see really easily. If you are able to sit in a swivel chair that spins very easily, it's got good bearings in it, it'll spin it can spin fast, it can spin for a long time. If you do that and hold a couple of weights out at your arm's length and then bring them in, you'll suddenly start to spin much faster. It's a very exaggerated effect. And so we can see this angular velocity changing just by changing a radius, which is very interesting. It's very unique.